From the ideas developed by the Greek philosophers, we have this atom as an indivisible unit of matter that still retains the properties of a particular form of matter. And then the ideas of Dalton developed our modern atomic theory. We've seen that subatomic particles were established by Thomson and Rutherford, and now we're going to start looking at modern atomic theory. One striking point about elements is the periodicity that they exhibit. Modern theory of atomic structure accounts for this periodicity in terms of electron arrangements in atoms. Before we get into the electron arrangements in atoms, we need to look at a few ideas in physics and realize that in the first 30 years of the 20th century, there were some key experiments carried out which classical physics or Newtonian physics could not explain. A new theory known as quantum mechanics was developed to account for the behavior of light in atoms. Quantum mechanics deals with atomic and subatomic particles, which are very different from the everyday macroscopic world that we're used to examining. So some questions to consider are things like, why do we get colors? And why do different chemicals give us different colors? And shown here are line spectra for several different pure elements. And we can see that, while many of the same wavelengths of light are observed for these elements, they're not identical. And again, this all has something to do with electron structure. So we're going to first look at properties of light called electromagnetic radiation. All forms of light, sunlight, microwave oven rays, X-rays, the heat from your fireplace are all examples of electromagnetic radiation. Electromagnetic radiation is one way that energy travels through space, or one form that energy takes in traveling through space. And these waves have characteristics such as wavelength, frequency, and speed. The wavelength, lambda, is the distance between two consecutive peaks or troughs in a wave. The frequency, nu, is the number of wave cycles per second that pass a given point in space. And the speed of a wave is the speed of light, 2.9979 times 10 to the 8 meters per second, such that the speed of light c is equal to the wavelength times frequency. Now, as we decrease our wavelength, as we shorten our wavelength, our frequency becomes greater. If we look at the first wave shown here, we have 4 cycles passing through the same distance in space in 1 second, which is 4 cycles per second. The cycles in frequency are implied, so we have 4 inverse seconds, which is equal to 4 hertz. For the second wave, we have 8 cycles per second, or 8 hertz, which is higher frequency for shorter wavelength. And finally, we have, in the last wave shown, 16 cycles per second with that very short wavelength. So again, increased frequency. There's an inverse relationship between wavelength and frequency. The longer our wavelength, the shorter our frequency. The shorter our wavelength, the higher our frequency. The entire spectrum shown here for electromagnetic radiation, goes from gamma rays, which are very high energy, short wavelength, high frequency waves, to radio waves, which are very long wavelength, low energy, low frequency waves. In the electromagnetic spectrum, we also have visible light, which goes from 4 times 10 to the minus 7 meters to 7 times 10 to the minus 7 meters. This is a very narrow spectrum, part of the electromagnetic spectrum. The visible light range is typically expressed in nanometers, so 400 nanometers to 700 nanometers. At the end of the 19th century, matter was thought to exist as particles which had mass and could be specified by position in space, while energy such as light was described as massless wave, delocalized in position, which could not be specified. About 1900, Max Planck, a German physicist, observed and studied radiation profiles of solid bodies heated. Planck postulated energy could only be gained or lost in whole number integer values, with the quantity h nu. H here is Planck's constant, and nu, again, is the frequency of electromagnetic radiation. The value for Planck's constant h is 6.626 times 10 to the minus 34 joules times second. A system can transfer energy only in these whole number integer values, which are called quanta, or wave packets. Energy seems to have particulate properties as well. So the big deal about Planck's results is that energy is quantized. It occurs in discrete units with a size h nu. H nu is this packet of light energy, which we call a quanta. The next big development for atomic structure came from Albert Einstein, who proposed that electromagnetic radiation was quantized, and he viewed waves as streams of particles called photons, where the energy of a photon is equal to Planck's constant times wavelength, which is equal to Planck's constant times the speed of light over lambda. Einstein went on to describe the photoelectronic effect, which he won the Nobel Prize for in 1921. Observations of the photoelectronic effect led to the idea of the dual particle wave nature of light. The photoelectronic effect can be characterized by the following observations. Studies in which frequency of light varied show no electrons emitted by a given metal below the threshold frequency nu naught. Light lower than threshold frequency gives no electrons emitted regardless of light intensity, and for light with a frequency greater than the threshold frequency, the number of electrons emitted increases with intensity of light. Essentially, in order to emit electrons, we need to have enough energy to dislodge the electrons from the metal surface. If the wavelength of light that we're using, or wavelength of electromagnetic radiation that we're using is below the threshold frequency, no electrons will be emitted from the metal surface. As long as we are above the threshold frequency, we can emit electrons. Einstein also derived the famous equation, which is the special theory of relativity, which shows that energy has mass and that energy is equal to mass times the speed of light squared. Again, all of these observations led to the idea of the dual nature of light, where electromagnetic radiation and all matter, for that matter, exhibits wave properties and particulate properties. So we can treat electromagnetic radiation as a light wave or as a particle, and we can treat matter as both particles or as waves. Now, diffraction occurs in wave mechanics. Diffraction occurs when light is scattered away from a regular array of points or lines. We often see diffraction on the back of a compact disc. Scattered radiation produces diffraction patterns, which result in either bright spots from constructive interference or dark spots from destructive interference. Sometime in the late 1920s, scientists at Bell Labs directed a beam of electrons at nickel crystals and observed diffraction patterns similar to the diffraction pattern observed in a beryl crystal. This shows that matter and energy are not distinct. Energy is a form of matter, and all matter exhibits both particulate and wave properties.